Take 41. I'm only slightly exaggerating that. All right, so the exciting third in our trilogy on null hypothesis significance testing, is it completely baloney? Is it baloney? Is it completely invalid? Well, let's see why some people think so. All right. So when we last left our adventurous coins, they were getting mercilessly tossed by statisticians just for the sick joy of illustrating concepts like hypothesis testing. Now we're going to talk about why some folks out there think that null hypothesis significance testing is bunk, and why we use it anyway. Now this topic is a little bit esoteric and a little advanced, so if you're a brand new beginner, I would maybe skip this video until you've been doing it a while. The long and short is going to be that you need to understand hypothesis testing because everybody does it. But there's no need to confuse yourself if you're just getting up and going. Plenty of stuff to confuse you when you get to t-tests. So anyway, you'll remember from our last adventure the binomial distribution, which you see here for 8 repetitions of a coin flip. If we were actually to do this experiment, we would get something called a p-value, which is just the probability of getting a result as extreme or more extreme than the one we got. For example, suppose I flip a coin 8 times and got 7 tails. And that means only one time the coin came up heads. The probability of that is exactly, to 3 decimal places, 0.031. But that's actually not the p-value. The p-value is the probability of getting a result just as extreme or more extreme. For a one-tailed test, we would have to add the probability of getting 8 tails, which brings it up to 0.035. But, as we learned in part 2 of the null hypothesis significance testing saga, using one-tailed tests is bad because it robs you of the chance to refute a theory, and the only way science advances is by refuting theories. So, we also need to add in weirdness from the other tail of the distribution. And that brings the p-value up to 0.0703, which is no longer statistically significant because it's greater than alpha, which is 0.05. Just a reminder, alpha is the highest probability that we're going to call so weird if the null were true that we're going to say the null is not true. We're going to reject the null hypothesis. Okay, but here's the problem. The p-value is the probability of the data, the actual outcome of the experiment, if the null is true. The p-value is not the probability that the null hypothesis is true. The p-value assumes that the null is true. Said more properly, the p-value is the conditional probability of the data given the null. But to reject the null, what we really want is the probability that the null is true given the data. If you ever want to mess with a statistician and see their eyebrows scrunch up, just interpret a p-value as evidence against the null hypothesis. Try it, it's kind of fun. Which brings us to Bayes' theorem, which gives us the relationship between these two things. Now, I'll do a separate video on Bayes one of these days, but for now, let me fill in for A and B the symbols we use for the null hypothesis and the data. We'll just use capital letter D for the data. So this is exactly the same equation, but this will make it easier for you to track the null hypothesis and the data. The thing we have, the p-value, is this. But that leaves us with one equation and 3 unknowns. We don't know the probability of the null, we don't know the probability of the data, and we don't know the probability of the null hypothesis given the data. And technically it's that thing, the probability of the null given the data, that we want. So yes, hypothesis testing is logically invalid. Or is it? The person who more or less invented null hypothesis significance testing, Ronald Fisher, actually knew about this and wrote about it in his original papers where he outlined null hypothesis significance testing. And statisticians have been aware of it ever since. And at least since the 1950s, there has been a small but very vocal group of mathematical psychologists, and this is probably true in other fields as well, for all I know, who have strongly argued that we should not be doing hypothesis testing. Statistical significance is a farce, they say. So why do we still do it? Well, mainly because there are no good alternatives. People have advocated various other approaches in the past, like using confidence intervals and something called p-rep, which is the probability of replication, and Bayes factors, which is kind of the new kid on the block, the Bayes factor. But all of these turn out to have either the same or very similar weaknesses to null hypothesis significance testing. Confidence intervals, for example, turn out to be just null hypothesis significance testing turned into an inequality equation. Mathematically, they're actually the same thing. A significant p-value implies that somewhere a statistic lies outside another statistic's confidence interval. All right, well, you may have been thinking at this point, why don't we just use the p-value to solve Bayes' theorem for the thing we want, the probability of the null? And the reason goes back to those three unknowns that I talked about. So one equation in three unknowns is what is known as an inverse problem, also called an ill-posed problem. Inverse problems are actually very good for scientists because they create endless opportunities for debate and fashion and cults of personality among scientists. But one thing we can do is make some assumptions. That's actually one of our favorite things to debate, which assumptions we should be making. Anyway, let's make an assumption about the probability of the null. Let's say we got a p-value of 0.02, and let's assume that the probability of the null is 0.5, a 50-50 chance, like a coin flip. This assumption, by the way, is called a prior probability in Bayesian thinking because it's the probability prior to knowing the data. We also need to make some assumption about the probability of the data, and that probability actually has another hidden unknown in it. The probability of the data, that's this thing right here, is actually made up of the thing that we know, which is the p-value, this thing right here. That's the probability of the data if the null hypothesis is true, plus the probability of the data if the null hypothesis is false. Those two probabilities make up the total probability of the data. And they cannot be bigger than 1 because no probability can be bigger than 1, so the total probability of the data cannot be bigger than 1. All right, so for now, let's just assume that the probability of the data given the alternative hypothesis, H1, or, in other words, the probability of the data if the null is false, let's assume that that probability is 0.8, which lets us figure out the total probability of the data would be 0.82. Right? Because I said we had a p-value of 0.02, that's the probability of the data if the null is true. If the probability of the data if the null is false is 0.8, then the total probability of the data is 0.82. Now we can fill out Bayes' famous equation. And we get the thing we wanted, the probability of the null hypothesis given the data. The only problem is, what if I say beforehand that the null is super highly likely? Like the most likely thing, like 0.9. Because if the null is false, then my theory is false, and your theory is true. And you say to me, ha, the null is actually very unlikely, like 0.2. Why, it's almost certainly false, because if it's false, your theory is true, and my theory is false. See, different scientists can have different priors, and that makes the whole thing subjective, which is not what science is supposed to be. Remember that scientific objectivity doesn't mean that scientists don't have opinions or biases or whatever. It just means that if I measure something and say it's 3, you don't have to believe me. You can measure the same thing using the same method, and you should see the same result, 3. But with Bayes, two scientists can take literally the same data and get very different numbers. Not good. Now wait a minute. We used a small p-value, and we got a Bayesian prior probability, the thing we need to, a Bayesian posterior probability, the thing we need to validly reject the null hypothesis, that was also small. So what is the relationship between the p-value and the probability of the null given the data? Well, there is no single answer. There is a family of answers. But we can figure them all out for a range of assumptions. we have to keep two things in mind. Number one, that the probability of the experimental hypothesis, H1, is 1 minus the probability of the null hypothesis, H naught. Remember, that's because what we do when we do hypothesis testing is we divide the sample space into two sets, one that's consistent with the null and one that's consistent with the experimental hypothesis. And the total probability of the sample space is exactly 1, because the sample space is everything that can happen in the experiment. Number two, we have to remember that the probability of the data is the probability of the data given the null plus the probability of the data given the experimental hypothesis. Given all this stuff, we can figure out the relationship between the p-value and the probability of the null for any prior that we want. And so here it is. And oh my goodness, they're monotonic increasing functions. They've been hammering and hammering the frequentists for decades that the probability of the data given the null is not the probability of the null given the data. But it turns out that they're related by monotonic increasing functions. The p-value was transmitting information about the probability of the null the whole time. The calls were coming from inside the house. Notice how even in the worst case scenario, where the null is almost certainly true, that's this one right here. The probability of the null before seeing the data is 0.9, an almost certain true null. Even in that case, a small p-value implies a small probability of the null given the data. In the case of maximum uncertainty, the null has a probability of 50%, the alternative has a probability of 50%. The relationship between the p-value and the probability of the null given the data is the identity line. They are, in fact, exactly the same thing in that case of maximum uncertainty. And of course, if the null hypothesis were unlikely to begin with, well then, the probability of the null given the data then gets very tiny, even with relatively large p-values. Now, none of this is to imply that p-values are never misused or alternate approaches like Bayesian inference are not useful, or that there are no problems with null hypothesis significance testing. P-values are often misused. Bayesian inference is super cool in its own right and sometimes is better than null hypothesis significance testing. And null hypothesis significance testing pretty much led my field, psychology, and a whole bunch of related fields right into a big replication crisis where people were getting rewarded for false positives where the probability of the null was so high and the p-value so near alpha that the p-value was probably misleading scientists about the probability of the null given the data. I'll do at least one video on Bayesian inference sometime, when I understand it better, but I have no objection to Bayesian analysis. I'm not one of those frequentists who just dismisses it because the priors are subjective. But the bottom line is this. We still do hypothesis testing despite the adamant objections of many prominent scientists, because none of those prominent scientists has come up with an alternative that actually makes up for any of the weaknesses of null hypothesis significance testing. And we need something, or else people are left to rely only on the human mind, which is pre-wired to see patterns in randomness. Alright, so summing up, technically, yes, NHST, null hypothesis significance testing, is logically invalid. Practically, however, it's no different than predicting y from x in a regression model. And if you think Bayes factors are going to save us, then I would refer you to this cool blog. This particular blog post here is all about the Bayes factor, but just in general, Data Colada is a cool blog. If you are not familiar with it, it's kind of a fun read every once in a while, and some folks who think very deeply about statistics and about inference and science and how statistics works in science and all that good stuff. So anyway, just a plug for that. I have no association with the Data Colada folks. I like their blog, so I'm going to give them a little plug here. All right, that's it for now. That is plenty enough.